Far beyond the familiar terrestrial planets lies Uranus, the enigmatic ice giant. Shrouded in an ethereal blue-green atmosphere, Uranus stands as a sentinel at the solar system's edge. Discovered by William Herschel in 1781, Uranus challenged our understanding of the solar system's scale. Its discovery expanded our cosmic horizons, revealing a system teeming with icy moons and faint rings. Uranus, unlike its neighboring gas giants, possesses a unique characteristic. Its axis of rotation is tilted at an extreme angle. Around this tilted giant, a retinue of icy satellites performs an intricate celestial ballet. Ferdinand, a member of this celestial dance, orbits Uranus at a great distance, its path tracing a slow and deliberate waltz. These irregular moons, with their eccentric and inclined orbits, stand in stark contrast to the regular moons that reside closer to Uranus. The discovery of Ferdinand marked a significant milestone in our exploration of the Uranian system. Prior to the late 20th century, our knowledge of Uranus's moons remained limited. The advent of powerful new instruments ushered in a new era of discovery, revealing numerous faint moons. Studying these newfound moons provides crucial insights into the dynamical processes that shaped our solar system. In 2001, astronomers Matthew Holman, John Cavallars, Dan Milosavljevic, and Brett Gladman discovered Ferdinand. Using the Canada-France-Hawaii telescope, they meticulously scanned the region around Uranus. On August 13th, a faint, slow-moving object caught their attention, revealing Ferdinand. Its discovery added another piece to the intricate puzzle of the Uranian system. The discovery of Ferdinand was the culmination of a concerted effort by a team of dedicated researchers. Matthew Holman, John Cavallars, Dan Milosavljevic, and Brett Gladman were part of a larger collaboration. Their success stemmed from access to powerful telescopes and sophisticated image processing techniques. The team's meticulous planning and collaborative spirit were key to their success. Discovering a new moon requires painstaking analysis of vast amounts of data. Ferdinand, being a small and distant moon, reflected very little sunlight, making it difficult to detect. The astronomers used a technique called shift and stack to amplify Ferdinand's faint signal. This process, while computationally intensive, proved successful in revealing Ferdinand's presence. The team's careful analysis and persistence paid off. The discovery of Ferdinand represents a significant triumph for modern astronomy. It highlights the advancements in observational technology and data analysis techniques. Ferdinand's discovery adds another piece to the puzzle of the Uranian system. By studying these distant satellites, we can glean insights into the early solar system. Ferdinand traces a solitary path around Uranus, its orbit a testament to gravitational forces. Unlike the regular moons, Ferdinand belongs to a class of irregular satellites. Ferdinand's orbit is a highly eccentric ellipse, carrying it far from Uranus before drawing it back in. This elongated orbit suggests Ferdinand's likely capture origin. Ferdinand's diminutive size and extreme distance make it a challenging target for telescopes. Based on its faintness, astronomers estimate Ferdinand measures only a few tens of kilometers in diameter. Despite its small size, Ferdinand likely possesses enough mass for its gravity to mold it into a roughly spherical shape. Determining Ferdinand's precise size and shape would require more detailed observations. Ferdinand is thought to be composed primarily of ice and rock. Spectroscopic observations could provide valuable insights into its composition. Ferdinand's ice is likely dominated by water ice, with other ices such as methane and ammonia possibly present. The presence and relative abundances of these ices could provide clues about the conditions under which Ferdinand formed. Ferdinand's vast distance and diminutive size have prevented direct observation of its surface features. Its surface is likely heavily cratered, bearing the scars of countless impacts. Another possibility is that Ferdinand's surface has been modified by internal processes, such as cryovolcanism. A dedicated mission to the Uranian system could reveal the true nature of Ferdinand's surface. Ferdinand is a member of the irregular moons, characterized by their distant, eccentric, and often highly inclined orbits. This family portrait reveals a clear division between the inner regular moons and the outer irregulars. Ferdinand, with its chaotic orbit and distant location, fits within this latter group. By studying its properties, we can piece together a more comprehensive picture of the solar system's tumultuous early history. When comparing Ferdinand's orbit to those of its fellow irregular moons, a pattern emerges, revealing potential subgroups within this already distinct family. While all irregular moons share the traits of distant, eccentric orbits inclined to Uranus's equatorial plane, subtle differences in their orbital parameters hint at shared capture events or dynamical interactions that have shaped their current paths. One key parameter for comparison is inclination. Ferdinand, with an inclination of about 60 degrees relative to Uranus's equator, falls within a group of irregular moons known as the retrograde moons, as they orbit Uranus in the opposite direction to the planet's rotation. This retrograde motion further supports the capture hypothesis, as objects captured from the outer solar system are more likely to have retrograde orbits. Another important parameter is eccentricity, a measure of how elongated an orbit is. Ferdinand's orbit, while eccentric, is not as extreme as some of its irregular siblings. This suggests that Ferdinand may have been captured earlier in the solar system's history, when the giant planets were potentially less dynamically active, resulting in less chaotic capture events. By comparing these and other orbital parameters, such as semi-major axis and orbital period, astronomers can group the irregular moons into potential families, each representing a different capture event or dynamical interaction. Ferdinand, with its specific orbital characteristics, likely belongs to a subgroup of retrograde moons that were captured early in Uranus's history, their orbits subsequently evolving due to gravitational interactions with Uranus and other moons. While Ferdinand's small size and extreme distance make it challenging to study its composition in detail, comparing its estimated size and potential surface properties to those of its irregular counterparts offers some insights. Based on its faintness, Ferdinand is thought to be among the smaller members of the irregular moon family, but its size alone does not tell the whole story. Some of the larger irregular moons, like Sycorax and Caliban, show reddish hues in their reflected light, suggesting the presence of organic compounds on their surfaces. These compounds, rich in carbon and other elements, could be remnants of the primordial material from which these moons formed, offering clues about the chemical makeup of the outer solar system. While Ferdinand's surface composition remains unknown, its smaller size suggests that it may have experienced less internal heating throughout its history compared to its larger brethren. This lack of internal heat would have limited its geological activity, potentially preserving a more pristine record of its formation and early bombardment in its surface features. However, without more detailed observations, these remain educated guesses. A dedicated mission to the Uranian system, equipped with instruments capable of analyzing the composition of these distant moons, would be invaluable in confirming these hypotheses and revealing the true diversity of materials that make up this intriguing family of objects. The study of Ferdinand and its fellow irregular moons highlights the importance of comparative planetology, the practice of studying celestial objects by comparing their similarities and differences. While each moon possesses its own unique characteristics, their shared history as captured objects provides a common thread, allowing us to draw broader conclusions about the processes that have shaped the outer solar system. By comparing the orbits, sizes, and potential compositions of these moons, we can piece together a more comprehensive picture of the dynamical environment in which they were captured, the materials from which they formed, and the subsequent processes that have modified their surfaces over billions of years. Ferdinand, though just one piece of this intricate puzzle, plays a vital role in our understanding of the solar system's evolution. Its distant orbit, potential for a pristine surface, and membership in a distinct subgroup of retrograde irregular moons offer unique insights into the chaotic early history of our cosmic neighborhood. As we continue to explore the outer solar system, comparative planetology will remain an essential tool, allowing us to connect the dots between seemingly disparate objects and unravel the grand narrative of our solar system's formation and evolution. Ferdinand, a small moon in a distant realm, reminds us that even the faintest whispers from the cosmos can hold profound secrets about our place in the universe. Ferdinand, a tiny moon in the vast expanse of the Uranian system, might seem like an insignificant speck in the grand scheme of the cosmos. Yet this diminutive world and its irregular kin hold valuable clues about a pivotal chapter in our solar system's history, the era of planetary formation. The prevailing theory suggests that our solar system emerged from a swirling cloud of gas and dust known as the solar nebula. As gravity drew matter towards the center, the sun ignited, and the remaining material coalesced to form the planets and their moons. The inner, rocky planets formed closer to the sun, while the giant planets like Uranus formed further out, where icy materials were abundant. The irregular orbits of moons like Ferdinand challenged the traditional picture of planet formation. Their capture scenarios suggest a period of dynamic instability, a time when the giant planets migrated through the solar system, gravitationally interacting with and scattering smaller bodies. By studying the orbital characteristics of these captured moons, astronomers can reconstruct the migration patterns of the giant planets and gain insights into the conditions that prevailed during this early epoch. Ferdinand, with its distant, inclined orbit, stands as a testament to this early period of chaos. Its very existence challenges our understanding of planetary system formation and highlights the importance of studying these seemingly insignificant objects to unravel the complexities of our cosmic origins. The capture of an object like Ferdinand by a giant planet is a complex cosmic ballet governed by gravity and celestial mechanics. As Uranus moved through the early solar system, its gravitational influence would have perturbed the paths of smaller bodies in its vicinity, potentially capturing some into orbit. The likelihood of capture depends on a delicate interplay of factors, including the relative velocities of the objects involved, their masses, and their trajectories. A close encounter with Uranus wouldn't automatically result in capture. The smaller object's energy and momentum would have to be dissipated for it to become gravitationally bound. Several mechanisms could have facilitated Ferdinand's capture, including gas drag in the protoplanetary disk, gravitational interactions with other moons, or even collisions between smaller bodies that altered their trajectories. By studying Ferdinand's current orbit and comparing it to those of other irregular moons, astronomers can model these capture scenarios and gain insights into the specific conditions that led to its integration into the Uranian system. Furthermore, understanding the capture process of irregular moons provides insights into the distribution of smaller bodies in the early solar system. These captured objects represent a sample of the primordial material that was present during planetary formation, offering clues about the composition and evolution of the outer solar system. In the frigid depths of the outer solar system, where sunlight is a distant glimmer, the search for life might seem like a futile endeavor. However, appearances can be deceiving. Moons like Ferdinand, primarily composed of ice, could harbor vast reserves of water ice beneath their surfaces, potentially creating conditions suitable for life. Water, considered a fundamental ingredient for life as we know it, is surprisingly abundant in the outer solar system, often mixed with other ices like methane and ammonia. On icy moons, tidal forces from the host planet and radioactive decay within their cores can generate enough heat to melt some of this ice, creating subsurface oceans. While Ferdinand's small size suggests that it might not have experienced significant internal heating, its composition and history remain largely unknown. Future missions to the Uranian system could investigate the possibility of subsurface oceans on Ferdinand and other irregular moons, potentially revealing hidden reservoirs of water and expanding the habitable zone in our solar system. The discovery of liquid water on a moon like Ferdinand would have profound implications for astrobiology, the study of life beyond Earth. Even if Ferdinand itself does not harbor life, its potential as a water-rich world highlights the diversity of environments where life might exist and underscores the importance of exploring these uncharted territories in our search for life beyond our planet. Ferdinand, a small, distant moon, serves as a potent reminder of the vastness and mystery that still shroud our solar system. Its discovery and subsequent study have opened up new avenues of research and challenged our understanding of planetary formation, orbital dynamics, and the potential for life beyond Earth. Despite its scientific value, Ferdinand remains a largely unexplored world. Its small size, extreme distance, and the challenges of reaching the Uranian system have so far limited our ability to study it in detail. However, as technology advances and our understanding of the outer solar system grows, Ferdinand and its irregular kin will undoubtedly become targets for future exploration. A dedicated mission to the Uranian system, equipped with advanced instruments, could provide unprecedented insights into Ferdinand's composition, surface features, and potential for harboring water. Such a mission would not only enhance our knowledge of this intriguing moon, but also contribute to a broader understanding of the outer solar system's formation and evolution. Ferdinand's story is far from over. This distant, icy world, once lost in the vastness of space, now beckons us to explore its secrets and unravel the mysteries it holds. Its discovery serves as a testament to the power of human curiosity and our unwavering drive to explore the cosmos, pushing the boundaries of our knowledge and inspiring future generations to reach for the stars. In the grand tapestry of the cosmos, Ferdinand might seem like an insignificant thread, a tiny moon orbiting a distant ice giant. Yet, its discovery and study have sparked curiosity, challenging our assumptions and highlighting the wonders of our solar system. Ferdinand's story is a testament to human ingenuity and our unyielding thirst for knowledge. Its discovery, made possible by advancements in telescope technology, highlights our progress in observing the cosmos. What was once a faint glimmer is now a celestial object of scientific inquiry. Its existence forces us to re-examine our understanding of planetary formation. Ferdinand's legacy extends beyond its own icy realm. Its study provides insights into the chaotic early history of our solar system. By piecing together the orbital histories of these captured moons, we understand the processes that shaped our cosmic neighborhood. Ferdinand's potential as a water-rich world fuels our imaginations and drives us to explore the possibility of life beyond Earth. The search for extraterrestrial life finds new impetus in the study of icy moons like Ferdinand, reminding us that the conditions for life might exist in the most unexpected of places. Ferdinand's story is just one chapter in the ongoing saga of cosmic exploration, a story that began with our ancestors gazing up at the night sky and continues today with robotic emissaries venturing into the unknown. As we delve deeper into the cosmos, driven by an insatiable curiosity and a desire to understand our place in the universe, we are constantly confronted with new mysteries, new challenges, and new opportunities for discovery. The exploration of our solar system is far from over. In the coming decades, ambitious missions will venture to the icy moons of Jupiter and Saturn, seeking evidence of subsurface oceans and the potential for life. Other missions will target Uranus and Neptune, those distant ice giants that hold clues to the formation and evolution of planetary systems. And as technology continues to advance, we can envision a future where human explorers set foot on these distant worlds, conducting first-hand research and pushing the boundaries of human knowledge. Ferdinand, a small moon in a distant realm, serves as a beacon, reminding us that even the most seemingly insignificant objects in the cosmos can hold profound secrets. Its discovery has expanded our understanding of the solar system and inspired us to reach further, to explore bolder, and to never stop asking questions about the universe around us. The cosmos is vast, mysterious, and full of wonder. And it is through exploration, driven by curiosity and fueled by imagination, that we will continue to unravel its secrets and unlock its mysteries for generations to come. Ferdinand's story is just one chapter in the ongoing saga of cosmic exploration, a story that began with our ancestors gazing up at the night sky and continues today with robotic emissaries venturing into the unknown. As we delve deeper into the cosmos, driven by curiosity and a desire to understand our place in the universe, we are constantly confronted with new mysteries, new challenges, and new opportunities for discovery. The exploration of our solar system is far from over. In the coming decades, ambitious missions will venture to the icy moons of Jupiter and Saturn, seeking evidence of subsurface oceans and the potential for life. Other missions will target Uranus and Neptune, those distant ice giants that hold clues to the formation and evolution of planetary systems. And as technology continues to advance, we can envision a future where human explorers set foot on these distant worlds, conducting first-hand research and pushing the boundaries of human knowledge. Ferdinand, a small moon in a distant realm, serves as a beacon, reminding us that even the most seemingly insignificant objects in the cosmos can hold profound secrets. Its discovery has expanded our understanding of the solar system and inspired us to reach further, to explore bolder, and to never stop asking questions about the universe around us. The cosmos is vast, mysterious, and full of wonder. And it is through exploration, driven by curiosity and fueled by imagination, that we will continue to unravel its secrets and unlock its mysteries for generations to come.